Hello and welcome to this video tutorial for the nuclear reactor design course. In this video we are going to be looking at some example questions involving gamma interaction and dosimetry. The first example question we will do is about gamma interaction. A beam of gamma ray with the energy of 1355 kiloelectron volts passes through materials M1, M2, and M3 with the attenuation coefficients of 0.1, 0.2, and 0.3, and they each have the thickness of x1, 2, and 3. We want to find the thickness of each material so that beam 0 is reduced by 30%, beam 1 is reduced by 75%, and beam 2 is reduced by 60%. We can use the exponential decay formula to find the flux of the beam after it has traveled through X amount of the material. First, we are going to be looking at material 1, which has an attenuation coefficient of 0.1, and we are looking to decrease the flux of the beam by 30%. We are going to assume that the initial flux of beam 0 was equal to 100, so after being decreased by 30%, the flux after passing through a thickness of x1 will be equal to 70. Plugging those values in with the attenuation coefficient of 0.1, we get this equation here. After rearranging the formula to solve for x, we see that the thickness x1 is equal to 3.566 meters. Material 2 has an attenuation coefficient of 0.2, and we are looking for the thickness x2, which will decrease the flux of beam 1 by 75%. Again, we will make the assumption that the initial flux was equal to 100, so after being decreased by 75%, the value of the flux will be 25. Plugging in the attenuation coefficient of 0.2, we have this formula here, and after rearranging and solving for x, we see that the thickness x2 is equal to 6.931 meters. Finally, we are going to repeat the process for material 3, where we are looking for a thickness x3 to decrease the flux of beam 2 by 60%. Material 3 has an attenuation coefficient of 0.3. After following the same steps as the last two examples, we can see that the thickness x3 is equal to 3.054 meters. The second example we will be looking at is about dosimetry. A cesium source of 1 curie and gamma energies of 662 kiloelectron volts is placed in a cube of 75 centimeter cubed of material with a density of 5 grams per centimeter cubed. We assume all gammas emitted from the source are fully absorbed in the cube media. First, we are going to calculate the total energy per second transferred to the medium. Then, we will calculate the absorbed dose rate in the cube. Then, we will calculate the corresponding equivalent dose rate. And finally, we will look at the total absorbed dose and dose equivalent for 1 hour. First, we are going to convert the activity from curies into becquerels, where 1 curie is equal to 3.7 times 10 to the 10 becquerels. To calculate the amount of energy being released per second, we are going to multiply the activity, which is in becquerels, which is essentially decays per second, which also is equivalent to gammas per second. We're going to take that number and multiply it by the amount of energy per gamma to get a value for the amount of energy being released per second. After multiplying the activity by 662 kiloelectron volts per gamma, we get a value of 2.449 times 10 to the 13 kiloelectron volts per second being released. We want our answer to be in joules per second, so we are going to convert our energy from kiloelectron volts into joules, and we see that our answer on how much energy is being released per second is 3.987 times 10 to the negative 3 joules per second. For the next part of the question, we want to calculate the absorbed dose rate in grays per second. First, we have to note that 1 gray is equal to 1 joule per kilogram. Since we already have the amount of energy being released per second in joules, all that's left is to find out how much mass we have in the cube. To find the mass, all we are going to do is multiply the density by the volume as given in the question, and we can see that the mass of the cube is equal to 0.375 kilograms. After dividing the energy release rate by the mass, we are given the absorbed dose rate of the cube being 0.010632 grays per second. For the third question, we are going to be looking at the equivalent dose rate of the cube given that the quality factor of the gamma rays is equal to 1. The equivalent dose rate, H, is calculated by multiplying the dose, D, by a weighting factor, which is W. Since our weight factor is 1, the quality of the gamma rays, we see that the equivalent dose rate is equal to our normal dose rate. This means that the equivalent dose rate is also equal to 0.010632 grays per second. The last thing we will be looking at is finding what the total absorbed dose and the dose equivalent is for 1 hour's time. Dose rate and normal dose rate are the same. The equivalent dose and dose for 1 hour will be equal. To get the total dose, we multiply the dose rate, which is in grays per second, by the time of 1 hour converted into seconds for the answer of a total dose of 38.2752 grays. This will conclude the tutorial.